be learning a lot about machine learning, how, computer vision, how machine learning and deep learning is employed, especially for image and video analysis that comes under computer vision. We'll also talk about few challenges, applications, and different segments where machine learning can be applied. So let's start with it. So before I dive into computer vision and deep learning and a lot of different difficult concepts, let me just give you the basics of what machine learning is. Most of you might already know it, but still, rounding up, machine learning is basically providing your machine or your computer the ability to learn from data to generate predictions and insights. So it is a very simple way where your machines learn from past data. They try to understand the behavior, they try to understand the patterns, understand the relationships, and based on that, they predict or they generate stuff. This is a heavy data-driven technology. Machine learning heavily depends on data, and when you move ahead with tasks like deep learning, they are much more dependent on data. So when we talk about the machine learning workflow, when you go towards processing any kind of machine learning algorithm, be it related to computer vision or be it related to NLP or be it related to any other technology, the workflow kind of remains the same. So the workflow involves, the first part of the workflow involves data retrieval. So when it comes to image and video, this data retrieval task would involve capturing images, collecting all sorts of images for your required task. So let's say for example, you have to perform a very basic task, which is the task of image classification. So I give you an image and you have to tell me whether it is an image of a dog or not, right? Now, this is a very simple image classification task. When you want to build your machine learning model that is capable enough to do this, the first part of this process would involve collecting lots and lots of images of dogs and labeling them by saying that these are the images which are of different kinds of breeds of dogs and these are not. So this data retrieval process becomes very essential and is one of the most crucial steps because the more data you have, the better your models are going to turn out to be. The second step of any machine learning workflow involves data cleaning and transformation. So now that you have captured lots and lots of images, there might be lots of images which might be blurred or which might have very low intensity or which are not clearly visible, and they might confuse the model. So you want to actually clean out noisy data and you want to keep only clean data so that your model understands clearly that, this is what is the correct data and the correct label. Now, when you clean your data, you would also want to convert these images into numbers. Since machine learning is heavily dependent on statistics and maths, all sorts of machine learning algorithms works with numbers. So different kinds of data input streams that you get, may it be text, video, audio, images, all sorts of input streams, they need to be converted to numbers. So next, your task becomes to convert your images into numbers. We'll talk about how different kinds of images and videos can be converted into numbers and processed via different ML and deep learning algorithms. But once you have converted your data into numbers, then comes the real part of actually training your model. You pick up particular machine learning or a deep learning model based on your analysis and study, and you train your model with your image data and you allow it to understand, to go through multiple iterations, to let it learn properly that this is what it is going to predict. Then you evaluate your model. You want to see how good your model is doing. So you keep a test set and you evaluate your model on certain sets of images. And you try to find out how good your model is doing or is there a scope of improvement. Now that you have evaluated your model, right? So you have gone from the process of data retrieval to your model evaluation. All of this is only worth it if you're going to deploy it somewhere, right? When I say model deployment, it means that it is going to be used by a particular requirement. So when you guys start work, some of you might already be working, some of you might not be working. So when you are working in a company, you have different projects that go into production, where actually customers are going to use the work that you do. So all of this work that you did, basically taking it towards the customer so that let's say you build a complete website where if a customer uploads an image of a dog, it can give an output saying that, yes, this is an image of a dog. And if it uploads some other image, it says this is not the image of a dog. So this entire production workflow of taking it to production, I just gave a very simple example of image classification. This dog identification task may not be needed in any company. So there are lots and lots of other applications that we'll talk about, but basically this entire flow more or less remains the same. You will definitely have advanced stuff that comes in each of these steps. Some of these steps might be very specific when it comes to different kinds of data, but this entire flow you will have to go through if you take any sort of input data. So there are different types of machine learning algorithms. So these involve supervised learning, unsupervised learning, and reinforcement learning. So in very simple language, supervised learning is the form of machine learning where you provide label data while training. So like for the example of image classification, we actually told the model that, see, these are the images of A class and these are the images of B class. So when you actually give them with the target label and tell them that, okay, look at this and then learn how to predict, it comes under supervised learning. But when you do not give the final label, when you say that I am just giving you this data, just let me know whether this is an image of a dog or not, and I'm not going to give you any sample data to learn from. So you have not given the model any sort of label data. It is just using its understanding of patterns and features and everything to figure out whether it is a proper prediction or not. Then it becomes an unsupervised model. Reinforcement learning is trained by continuous feedback mechanism. So a lot of tasks in robotics where the task is to pick up an object or the task is to visually understand a certain image. All of this comes from reinforcement learning. Why is this important? Because now when we talk about computer vision, we'll be talking about different algorithms such as CNNs, RNNs, GANs, autoencoders. We'll talk about them in detail, but we would want to understand that which of them actually come under supervised bucket or which of them actually come under unsupervised bucket, and how to evaluate them separately. So there are lots of applications of machine learning. Some of these applications involve computer vision, some of them don't. So a lot of applications like image recognition, self-driving cars, medical diagnosis, these involve computer vision tasks. Some other applications such as speech recognition, virtual assistants, sentiment analysis, all of these require NLP-based technologies. Some other standard applications like search engines, stock market price prediction, weather forecasting involve a lot of numerical data. So in this particular masterclass, we'll be focusing a lot on computer vision related applications and the computer vision related modeling tasks. So let's start by talking about image and video analysis. So in very simple terms, image and video analysis will look at different kinds of tasks that involve images and videos. So tasks such as image recognition, where you want to recognize a particular image segmentation, dividing a particular image into different segments, image captioning, identifying textual description for a particular image parsing, object detection, and video segmentation. So these are different kinds of tasks that you can do under image and video analysis. Now, using computer vision, a lot of these tasks are possible, and we use deep learning tools to perform these kind of tasks. So we'll be looking at different kinds of deep learning models, such as CNNs, GANs, VAs, to perform this. I'll be talking about in brief some of these models so that you'll get to know about how these models work and what kind of task do we do with them. So let's start by talking about what computer vision is. So now you would have seen that computer vision involves understanding the content of, understanding the content of digital images and videos, right? All sorts of image and video analysis we do using computer vision. So now this computer vision not only involves just processing your images, but it would also involve the hardware system attached to it. So when you say, for example, one real-time application of computer vision comes as video surveillance or traffic jam analysis, right? So let's say you want to capture real-time video of a particular traffic jam and you want to get the positioning of cars in that video. Now, for that to work, you would first want to have CCTVs set up in that particular area, right? So this hardware setup of setting up CCTV so that they cover each angle and you can get proper video surveillance all time. They should be working the entire day, the entire night, and should be storing your data in some cloud resources. And then you should be having a software which can keep on processing that kind of data so that you keep getting numeric features out of those images and videos. And then you use AI-based models to process it and to get the relative captioning, such as object detection tasks. And then you analyze them and generate insights out of it. So this not only computer vision not only involves just processing that data, but it involves collecting that data from the source, which involves the hardware setup, to finally analyzing them, storing them, and this involves different brackets of tools, such as cloud computing, AI, cameras, and a lot of different other tools that are involved in this. So some of the popular tasks we have already seen earlier: object detection, object recognition, object classification. So there's a lot of difference between these tasks. So object recognition would just focus on identifying whether a particular object is available in a video stream or a image, while object classification task involves actually not only just saying that whether an object is present or not, but it also tries to identify what are the different objects that are present in a particular image or a video. Object detection task would also look at the localizing factor, and it will give you the boundary boxes, which will tell you where a particular object is present in a particular image or a video. So these information, such as identifying its positioning, identifying its relative objects, all of these come under extracting information from images. And this kind of technology is called as computer vision. So this very simple example shows how just finding out whether what this image belongs to which class, that this image is of a cat, is a simple classification task, where let's say you have two different classes, cat and dog, and you want to actually classify this image into cat or dog, and so your model has rendered cat saying that this is the image of a cat. Now, when it comes to localization, you also identify boundary boxes against it. So you actually identify where in that particular image your cat lies in. When it comes to object detection, you try to identify what are the different objects. So you see that there's a cat, there's a dog, there's a duck, the different objects that are present in that particular image. And when it comes to instance segmentation, you actually try to identify the actual boundary against it, and so that you can actually take it out of that image and you can process it as a separate instance. So these are the different types of tasks that come under computer vision. Yeah. So computer vision is very similar to how pattern recognition works, because all of this image and video data is sent to deep learning models, and then you try to identify patterns from it. So when I say this task of classification, it has to identify whether this is an image of a cat by finding out certain patterns that it has learned from the training set of a cat image. So it has to find out the whiskers, it has to find out the big eyes, it has to find out how ears of a particular cat are shaped, whether it has four legs or not. It has to actually identify those features to distinguish that what animal it is. So these kind of patterns that it learns by looking at the data, it then tries to apply to a certain images to get its final output. It tries to learn how these pixels are connected. So usually deep learning models take in lots and lots of data, and then they learn these feature representations and these patterns, and then they transform it into mathematical equations so that further on you can incorporate these patterns into these mathematical equations and can generate insights out of it. Okay. Now, there's a difference between computer vision and image processing task. It kind of looks and sounds very similar, but computer vision and image processing tasks have certain differences in between them. Image processing tasks mostly involve modifying the image. So it involves changing the brightness, changing the contrast, applying filters, cropping an image, reducing noise in an image, which we can also do with our phones, our cameras and our video editing, photo editing softwares. They allow a lot of these applications. While computer vision models, they can actually generate insights from images and they actually understand what is the content of a particular image. So, if I explain it in very simple terms, when you give your phone an image of yourself with some background, and let's say you want to clean the background and you want to crop the image to remove some people who are there in the background, and you want to enhance the brightness and you want to change the hue and contrast, you can do all of it using your photo editing tools and video editing tools without even the tool or photo editing software knowing that this is an image of a human which has a background which has other humans, which is very less bright. The photo editing software has no connection or has no knowledge of what is the content of this particular image, and hence it is not capable of generating any insight out of it. But with computer vision, since it understands the content, it can actually generate a lot of insights. It can tell you a textual description saying that a human is standing in front of a building with two other humans in the background. It can give you the color description that the human is wearing a red colored shirt with brown building in the background. So all of this understanding can be applied in the form of computer vision. So earlier that we have talked about different kinds of models that we use for computer vision tasks. Let's look at one of the basic model that has been into consideration for a very long time. So CNN have been used for performing lots of computer vision tasks for a very long time, and they're still being used in a lot of applications as either as a part of it or as a whole model itself. In very simple language, CNNs are type of deep learning model which are specifically designed for images and videos, right? So they extract meaningful information and features from input data. So if you just look at the CNN network that we have over here, this particular input image, you have different kinds of layers in your CNN network. You have a convolution layer, you have a pooling layer. So each of these layers have different tasks attached to it. And then you have a flattened layer which will incorporate all of this learning into a single dimensional vector. And based on that, it will perform the classification. So the goal is to actually identify that out of three classes, Donald, Goofy, and Tweety, which of these this particular image belongs to. So this since this particular image belongs to Tweety, we get a higher probability value there. Now, how does this model learn that this is the image of it? It would have seen all other images. So let's say this model is trained with thousand examples, each of these three classes, right? So what it will do is because it knows the label for each of these classes, for each image that you give it, it will try to extract certain features and it will try to understand that, because of these features, this is the label that we are getting. So let's say you give it one image and it has extracted certain features, and then you gave it the label that this belongs to Tweety, right? Then you gave it another image and it extracted some other features, and then it understood that okay, these features belong to Tweety. So when it sums up its intelligence from all 1,000 images, it now knows that what are the features that correspond to this particular class. And when a new image comes in, it tries to look for those filters. And when it gets them, it classifies them correctly. So there's a convolution layer in the beginning. This convolution layer basically goes across the image. So this convolution layer will have smaller matrices which will actually convolve. So when we say convolve, it basically in mathematical terms, it multiplies the smaller matrix to the actual 2D or three-dimensional matrix which is available for the input image. And when it convolves, it tries to multiply that filter into the actual image and tries to get the values for your convolution layer. The pooling layer will then sum up the values for each, let's say, a 2x2 boxes, so that it reduces the dimension and it captures only the most essential information from the convolution layer. This step is repeated multiple times, so you can have multiple CNN blocks. So in this image, let's say we have two CNN blocks in between. And once you combine all of these, you can flatten it, you can get a feature vector, and you can pass it on to a classification task. So CNNs work very similar to how visual processing happens in our brain. They are built on the concept of layers, and each layer has a separate goal of extracting features. They will apply these filters. So when I say they convolve across the images, they apply certain filters to your input data and they capture these patterns. Then the pooling layers will reduce the dimension and then they emphasize on the most important patterns. Then finally, your fully connected layer will extract your features. So a very simple CNN architecture will involve your input layer along with a convolution layer, which will convolve the pooling layer and then the fully connected layer, which can perform different kinds of classification and detection level tasks. There are a lot of applications of CNN. Some of these directly involve tasks like image classification, object detection, identifying and localizing different objects within a particular image, video analysis. So when we say we want to do a video surveillance, in that particular case, we want to identify the relative positioning of cars. We can use CNNs to actually localize and identify these images. Now we have seen how image-based tasks can be performed using deep learning technologies. Let's look at the task of video analysis. So video analysis focuses on recognizing temporal and spatial events in a video. So when we say it recognizes temporal and spatial events in a video, it means its goal is to understand the change in the scene. Its goal is to understand how a particular video is moving on, how the frames are moving on per second, and then process on each of these frames. So it divides your entire video. Let's say you have a video of 2 minutes. So it will divide your entire video into multiple frames, and then each frame is treated as a single image. So these video analysis systems, they can perform real-time monitoring. So they can identify movement patterns of, let's say, cars, or they are used in tools like smart parking, where you can actually identify the location of a particular car, and based on that, identify which parking spots are empty and they can be highlighted. They can be used for behavior related to monitored environment. So they, for example, your facial expression changes. So they can be used to understand how the facial expression changes and how that can be monitored to understand mental health. So all of these tasks can be done using video analysis. So it can also be used for analyzing historical data rather than doing real-time analysis. Some of the popular applications involved, such as monitoring traffic jams and then alerting in real time. Two others, like analyzing customer flow. So when there's a retail store, can involve video surveillance and it can actually understand how the customer flow is there on a particular day. And based on that software, if it sees that there are a lot of humans walking in the store and there's a lot of crowd in a particular section, then they can deploy their sales agents towards that particular section to maximize their sales. Then there are other scenarios such as facial recognition and even facial expression recognition to understand the mental health of a person, and smart parking. So all of these are different applications that comes to analysis. So as we already saw these applications like body posture monitoring, so identifying the posture of a particular person to figure out some kind of health issues that the person might have. Then there could be license plate monitoring. So based on if there's a proper connectivity of CCTV cameras across the highways, then it can also help in capturing thefts, where a certain car with a particular license plate can be tracked on the images, and using object detection tasks and also using OCR, where you actually try to identify character recognition in images. So OCR is the task where you try to identify characters in a particular image. So let's say I give you this particular screen, and if you take a screenshot of this particular screen, you will get an image out of it. Now, if you want to actually extract the text from this particular image, that this text is about video analysis application. So this particular text extraction comes in the task of optical character recognition, which means identifying characters from a particular optical image. So using optical character recognition and object localization together, we can actually solve anti-theft problems if there is a proper coverage of CCTV cameras and the license plate tracking can happen. There are a lot of different deep learning models that are employed for these different kinds of tasks, and large amounts of data can be tracked in both real-time and historical scenarios. So let's say license plate tracking, video surveillance for traffic jams, or facial recognition. These are some real-time tasks that happen on the go, right? But there could be a lot of experiments that need to be performed for historical scenarios where you want to analyze videos for historical data to actually capture and generate insights which can help you in monitoring your real-time systems. So those insights generation are done by performing deep learning on lots and lots of video analysis. So how does it work? So first we take the data from various sources. So your various sources will involve camera feeds such as CCTV footages. It will involve the video inputs, and then it will require for the model to capture this properly. It will need to have a complete coverage so that you can process the different angles and different frames to get the complete coverage of that particular video. Now that you have taken enhanced the data, you can perform your different tasks such as image detection, localization, object tracking based on the requirements. There are a lot of different pre-trained deep learning models already available. So you can perform tasks like transfer learning. We'll talk about transfer learning in a brief, but transfer learning will help you understand that how these large deep learning models can be used to perform your instruction specific tasks. So let's talk about feature extraction from images, right? Earlier we talked in the machine learning flow that each of these data sources, they need to be converted to numerical scenarios. And then based on that, you need to perform machine learning on top of that, right? So we need to convert different kinds of data inputs such as images, videos, audio, text, everything into numbers first. So how do we actually convert images into numbers? So if you can see in this particular image, the first one is an image of a letter 8, where the letter 8 is present in white color while the background is present in a black color. So this is a grayscale image. This grayscale image is basically, we are going to convert this into numbers, right? So in order to convert this into numbers, we want to store the images in the form of pixels. So these pixels represent the matrix of numbers that is available in the second image. Now, the pixels, the dimensions of the image will basically be the number of pixels in the image, and the value of those numbers, like what is the value of those numbers, they will show the brightness or intensity of the pixels. So in a grayscale image, since the pixel value ranges from 0 to 255, if an image is, as you can see, it ranges from black to white, right? So if you can clearly see the image, then all the values which are very closer to, for all the cells where the value is close to black, you have values which are less than, in between 0 to 10 or something like that. Values which are slightly more gray in shade have slightly increased intensity, and hence they are showing slightly higher values like 60, 70. And if you keep on increasing and in proper white, bright areas, your values are very close to 255. So this is a very simple representation of a grayscale image, where based on the intensity of your grayscale image, how black or how white your image is, you can actually design the number of a particular portion. And this entire matrix will represent the number of pixels in the image. And this number will completely generate your matrix, which will be a two-dimensional matrix for a grayscale image. You can further take as a two-dimensional input for your different models. So you can use it into your CNN networks, a two-dimensional, you can either flatten it out and use as a one-dimensional input vector, or you can keep it as a two-dimensional input vector and you can actually pass it on to a two-dimensional convolutional layer. But this is about the grayscale images. So when it comes to colored images, we represent it via three channels or matrices, so that each of those matrices will represent your intensity for your R, G, and B values, right? All the colors that we know are combinations of red, green, and blue, right? So if you, instead of this black and white image, if you have a colored image, in that particular scenario, you would want to have three different matrices, right? So the first matrix will have your intensity values for the red color. So in areas where the color is mostly similar to red, pink, brown, the intensity values will be higher. While in areas which are very remotely not connected to red, let's say if you mix green and blue, right? Then you get a color which does not involve red in it. Then in those areas, the value of this matrix would be 0. Similarly, you get another matrix which will have the intensity of blue green color, and then another matrix for blue color. So your feature dimensions will be x comma y comma 3, because you have three different matrices and x comma y are the two dimensions of your particular image. Now, in those cases, what happens is your feature vector becomes huge, right? So even if you have a resolution of, let's say, 144 across 144 or 256 across 256, then your entire number of pixels would become 256 into 256 into 3, which is like a huge input data to be fed into different deep learning models. And let's say if you have hundreds and thousands of such images, then it becomes even more complicated. So in those scenarios, usually the mean value of pixels is captured across the three different matrices. And then this mean value is then used to ensure that you get your final image, which is of the same dimension as your input image, and it gets processed. So you will get an x comma y dimensional image, which will have the mean values taken across the three different matrices. It is very similar to pooling, but instead in pooling, when you take a 2 cross 2 filter that applies on top of your convolution, here for each value of the matrix, you try get a mean value and then you incorporate it in the new matrix. Before going ahead, I saw a question which mentioned that do we need to have different softwares for different models? So just to answer that, when you want to train your different models and different sizes of data sets, you will need to have an incremental software for that, because let's say you want to use a simple GPU in order to process your images, the memory and the computational powers of that GPU might get limited, and you might have out of memory errors when you want to train on larger subsets of data sets. So you might need to have an increased memory size GPU with large computational powers and with large storage capacities. So based on the requirements and the size of your training data and your test data, you can decide the size of your softwares as well. Okay, let's move ahead. We earlier saw how we can extract features for images on both colored and grayscale scenarios. Now let's talk about something called as representation learning, right? One simple way is to actually convert these images into its pixel intensities and get the numeric representations, right? But after getting those representations, we need to process that data to get insights out of it, right? Representation learning is one such form of technology which will automatically extract feature patterns from data. It will automatically incorporate those latent features, those hidden features that are there in the data about how those whiskers are shaped or how a particular ear is shaped or where in a particular image can you find positioning of a feet or of a ear or of eyes. All of these hidden representations and interpretations are handled by using representation learning. So it will basically identify how your predictive model will perform by capturing how similar two particular images are by looking at their features and then finding out similar patterns. Or it can also identify what particular feature represents to what portion of the text so that it can help you with textual descriptions. So how does it work is it reduces high dimensional data to lower dimensional data. So a higher dimensional, three-dimensional data is lowered down to a two-dimensional data. And then based on those numbers, it becomes easier to identify patterns and anomalies. So basically, we tend to identify those hidden features out of the image, and we tend to make sense of those hidden features to understand those images better and then to generate insights from it. Okay. So there are a lot of supervised and unsupervised tools that are used for representation learning. We earlier saw how what supervised and unsupervised learning were. So supervised methods such as CNNs, multi-layer perceptrons are used to identify automatic patterns. We saw how convolutional layer convolves over the images and how pooling layer captures only the relevant aspects from the convolution. So those convolution and pooling layers together capture those relevant features and identify the patterns from the images. There can also be autoencoders and RBMs, which can also be used to identify feature patterns in an unsupervised manner. These autoencoders are used for converting these higher dimensional data into lower dimensional data, that is, encoding them into a two-dimensional vector or a one-dimensional vector, and then reconstructing those embeddings into a particular image so that after that reconstruction, it tends to identify which portion of the image is actually helpful. Let's talk about some of those applications of computer vision that we saw, right? We saw the applications of object detection. We saw the applications of image captioning, video captioning, object tracking. Let's look at some of those applications and see what they actually mean. So in very simple language, object detection is the task of identifying whether an object is present in an image, right? I give you an image with an image of a cat in it, and then your goal is to identify whether a cat is present in a particular image or not. Not only do you identify whether a particular image is present or not, you also tend to identify its relative position. That means what is its positioning with respect to other images? This has a lot of applications because not only in scenarios of static images, but when let's say you're building a program for a self-driving car, right? And you want to actually, so what happens with self-driving cars is it keeps on getting the visual representations of the road ahead of it, right? So then it keeps on getting those visuals, and its goal is to identify if any object comes in between. Because if an object will come in front of that particular car, it has to apply brakes and it has to stop. Or when it sees a red light, it has to stop. So it has to identify all those images. It has to identify that this traffic pole is showing red in color. It has to identify its location. It has to identify if a car is crossing from left to right in front of a particular self-driving car. And then it also has to identify its relative positioning with respect to itself so that it can apply brakes within a certain distance so that the car doesn't get hurt. So all of this understanding that whether a particular image is present or not, and if it is present, then what is its positioning in a particular scenario, or if you want to identify multiple such objects, because in case of self-driving cars, you have to simultaneously identify all the objects that are blocking your positioning, right? You will have to identify if a human is crossing. You'll also have to identify the speed if a human is crossing in front of your car, because based on that speed only you will have to decide that how long do you have to keep the brakes on, whether to switch off the car or keep the car switched on. All of this is achievable using object detection tasks. So now to perform this object detection, right, we use a model called as YOLO, you only look once. This was introduced in 2015, and since then it has become a state of the art model. It has shown immense capabilities in the task of object detection. And this is an open source model. That means even you can go look at its official documentation, download it, use it for your images and videos. It is extremely fast and has a high detection accuracy. It has shown to identify almost all possible objects with correct boundary box limitations. So let's look at YOLO, right? If you can see the image on the left-hand side, you can see that in order to work with YOLO architecture, you have to resize your input images to 448 cross 448. So even if you have higher resolution images, you will have to resize them to 448 cross 448 dimensions. And then those 448 cross 448 dimension images are passed on to CNN blocks. So you have convolution layer and you have a max pooling layer. So as we talked about pooling layer, right? Pooling can be of two major types. It can be max pooling or it can be average pooling. So average pooling will basically take the average of the filter that it has taken. So let's say it goes over a 2x2 block, then it will take an average of the 2x2 block and will reduce the dimension from 4 to 1. But if you look at max pooling, it will take the max value from the 2x2 block and will reduce the dimension from 4 to 1. So in cases of YOLO, you have convolutional layers and you have max pooling layers. And you also have the dimensions of those convolution layers and max pooling layers for YOLO, right? So as you can see, your max pooling layer is a 2x2 layer, which is applied on top of that convolution layer. And then you have your convolution layer of the dimension of 7x7x64. So first, a 1x1 convolution is applied, which will reduce the number of channels. That means you want to flatten out your input because your colored images have 3 different channels. Then after that, you have a 3x3 convolution so that you can get a cuboidal output, right? Now, along with that, you have 24 different convolution layers. So it's not only one single convolutional block, but 24 different convolutional blocks with different dimensions in it, and each block having different convolution sizes of different convolutional layers. So the first one is just one convolution layer, then you have subsequently incremental convolutional blocks, right? You have an activation function of ReLU, which is used, and the final layer uses a linear activation because in the final layer, you want to actually identify first whether an object is present or not, and if present, then what is its location. Then there are certain additional techniques such as batch normalization, dropout. Then you have to regularize the model. These are certain standard deep learning overfitting handling tools that you do in order to handle overfitting in your cases, right? So this is the standard convolutional architecture that YOLO uses, and it has shown immense applications. This convolutional architecture will also have residual blocks in it. So when we say residual blocks, and it will have skip connections as well, that means it's not only linearly structured, but some of the layers from the right-hand side might have direct connections by skipping some layers in between. So let's say layer number 4 can have a direct connection with layer number 1 by skipping the layers 2 and 3 in between, while layer 3 is also connected with layer 4. So it has all these advanced capabilities by incorporating the basic structure of CMNs, but also ensuring you get other patterns and other representations so that you can actually perform this task. YOLO has a lot of applications. In general, when I say YOLO applications, it mostly targets to the applications of object detection tasks because YOLO is one of the standard algorithms that is used for object detection tasks. So it has applications in healthcare where, let's say, you want to use it for localizing organs. That means a lot of CT scanning or imaging, medical imaging tools. If you use YOLO based technologies, it will help you identify the positioning of a particular organ and also the size of a particular organ per se. It has its applications in agriculture where in dense agricultural scenarios, it helps you identify the right fruit which can be harvested and thus helps saves a lot of time for farmers. It has a lot of applications in self-driving cars, which we have already discussed. Then it has a lot of applications with security. That is when it comes to video surveillance and license plate monitoring. So we've already discussed how license plate monitoring can happen, how object tracking happens, and when a car is moving, it can use optical character recognition to identify the numbers and the letters from the license plates. And then it can keep on tracking the boundary boxes of that particular object. That means its relative positioning to identify anti-theft scenarios. Along with object detection, object tracking is the task of identifying objects in a video. Like how object detection happens in images, object tracking happens in a video, where for each frame, you keep on identifying where that particular object is set. And then you interpret them as a set of trajectories. That is how that particular object is moving across the frames of a video. So very simple application involves video tracking, which we saw as in cases of license plate monitoring, right? Now, object movement speed is one of the biggest hurdle that comes with object tracking scenarios. because let's say that car can be moving at different speeds and your frames can be changing at different frames per second, right? So your model should be capable enough to handle the variation in speed of a particular object. It should also be capable to handle the background distractions. So let's say when your camera is not moving with the car, right? You might have cameras, CCTV cameras in place, let's say at 2 kilometers on the highway. At every 2 kilometers, you have a CCTV camera in place, right? So when that car moves from point A to point B between two cameras, there might be scenarios that there's some other car that's blocking the view from the CCTV angle, right? Or there is some XYZ building or anything that might be blocking the view. So all these kind of background distractions might be a hurdle in case of object tracking, because then you might lose sight of that particular car, right? Then there could also be scenarios such as multi-size and multi-aspect ratios. You might have license plate numbers which are not very clear, which are smaller in size, which are painted in a different color, and then that might not be, your model should be trained and capable well enough to handle all these various scenarios. Now, multiple object tracking with bounding boxes can also be done using object tracking tasks. So you can not only track just one single object, you can also track the relative positioning of different objects on how they are moving in a particular video, like how it happens with self-driving cars. And then you can allow your model to learn from those capabilities. To do this, we use models such as fast RNNs, autoencoders, GANs, and recently there are a lot of improvements with generative models that have come up that help you identify those scenarios. Let's talk about image captioning. Image captioning is another application when it comes to computer vision. Very simple terms mein, this image captioning task is the process of generating a textual description for a given image. So you have been given an image and you want to identify what that image is all about. So you want to generate a textual description. Like for example, I give you an image of a landscape and you will generate a textual description saying that it involves mountains, rivers, it involves greenery, it is a lush green forest, or it belongs to lush green mountain area. So all this textual description that comes from a particular image, that is the task of image captioning. So in cases of image captioning, you're not only working with image-based models such as CNNs, you'll also have to work with text-based models such as RNNs and transformers, right? So you'll have to look at end-to-end sequence-to-sequence problems because text works in a sequential way. And you'll have to convert these sequence of pixels to sequence of words. You'll have to generate text out of these images. So there are certain tools that are used in order to generate text out of these images. So let's say you have a particular scenario where you want to apply an RNN to a word as well as an image. Instead of using a CNN for an image, you use recurrent neural network blocks, both for words and images, and you process them together in order to get your final output. This is conditioning by injecting the image. That means you are injecting the image into the same model that processes the words. So this is injecting the image, right? This is one of the ways in which you can perform image captioning. Another way that you can perform image captioning is by merging the image. So that means you are not passing the image as an input to RNN blocks, but you are passing the image after you get the output from RNN blocks, right? So these kind of tools which involve merging the image after getting the output is another way where you can perform image captioning. So this is one model that basically looks at performing image captioning. So on the left hand side, you can see an input image which captures different giraffes. And on right hand side, you can see that you have the output tokens. On the top right hand side, topmost side, you can see that you have your output token start, giraffe standing, end. So giraffe standing is the caption for this particular image, right? And how it is being done is you already have a pre-trained CNN model, which is trained using ImageNet dataset. So ImageNet dataset is one of the most widely used datasets for such cases. So you can have a pre-trained CNN model, which is already available online. You can download it. You can apply feature vector you can convert this input image to your, after applying the CNN model, you can get the output from your convolutional and pooling layers. And then after you get the output, you pass it on to your LSTM blocks, which is very similar to RNN blocks, along with your input from the text values. So you have textual embeddings and you have image feature vectors, which are passed together as an input to your RNN blocks, where you get the textual output. This kind of method is called as image caption. Now, recently, you would have heard of generative models such as DALI or models such as Midjourney, which are capable of generating images from text. So that involves the reverse process of this, where if I give you a text saying giraffe standing, you will actually be given, the output will be an image of giraffe standing. So that is very complex process, because extracting textual information from images is slightly easier when it comes to actually generating an image with different colors, different pixels, different sizes of giraffes, you know, placed all together, because then you have to look at the relative positioning, the relative color, everything together. So these DALI based models, which have been launched by OpenAI, takes care of that, and it generates images from textual prompts and textual inputs. So these DALI based models also uses something like a textual embedding models, and they also use something like variational autoencoders and diffusion based models. So the goal of these models is to ensure that you have a model that understands the image description, that also understands the textual description, and that is capable enough to converting one onto the other. Then there's another task which comes out to be video captioning, right? Video captioning is a very famous task. You would see all these live YouTube videos that you watch. If you turn on the captions, you get live captions on your videos, right? That is the task of video captioning. Some of them might have already uploaded the captions, right? So some of these videos that are uploaded on YouTube or some other websites, they already have captions in between. So in those cases, those captions are just mapped onto different frames and they are saved all together. But in some other cases where the captions are not actually provided by the person who has uploaded the video, YouTube has inbuilt software where it can help you generate those captions, right? They might not be 100% correct, but they still help you get the context of what that video was about. So in those cases, it is automatically describing each and every text that has been spoken in a particular video. Along with that, you can also use it to generate explanation about a particular video, right? So in those cases, you need to extract more features than image captioning, because each video has a lot of image frames, right? So basically it has a lot of images. Like for example, if you keep taking screenshots every 1 second in a particular video of, let's say, 60 seconds, you'll have 60 different images which have slightly different parameters every time, right? Now you cannot do it at 1 second, because 1 second is a huge time for you to keep changing frames. So when it is done by the models, this duration is even reduced and you get multiple frames. So let's say you get about 100 frames per second, right? Or 40 frames per second. So when I say 40 frames per second, the screenshot that is happening at every 1 second, that's happening 40 times in 1 second, right? So if you have a video which is 60 seconds long, you have 40 cross 60 individual images, each having different explanations. And your goal is to now perform a video captioning by taking into consideration all of these images together and then deciding out your output. So the kind of models that are used is the video feature extractor, which can generate video features specifically, and then fusioning these features so that you can have a textual output from the generated model. We have talked about different tools like video captioning, image captioning, object tracking, object detection. We've talked about computer vision. We have talked about its applications. We've talked about YOLO. We've talked about different machine learning and deep learning tools that are used for video analysis. And we also saw the machine learning workflow, right? So you have processed your features into your pixels using CNNs. You have modeled by using smart models like YOLO, and now your goal is to basically deploy those models. in a very standard nutshell, machine learning and deep learning models are deployed by using some standard tools that remains almost similar for almost all kinds of machine learning applications. They might change based on the requirements, like how if you're working with a deep learning model as compared to a machine learning model, you might need to change your memory requirements of your GPU or of your machine where your model is going to get hosted, but standard procedures remain the same. So you have to integrate it to a web framework where your customer can actually access your model, right? So let's say you have an object detection model where, or a image captioning model, right? So you will have to have a web framework where if you upload your image, you can get a textual output. You have to deploy it to a server because your website needs to have a connection to a server so that it can send that image and it can get the text and then it can render it on visual. So that hosting services, you can use any of the existing cloud-based services, or if you belong to a huge company, then you can actually use some of your existing GPUs. Along with that, you need to also ensure the kind of requirements, hardware requirements that you are going to be using and software requirements based on your task, whether your task is related to video or images, the kind of training data it will need, all this needs to be taken into consideration. So a standard machine learning deployment strategy involves your data preparation, training and evaluation and deployment, which is a part of your machine learning framework. But once that is done, right, you need to constantly monitor the performance of your models because your model performance cannot degrade. So then it becomes no sense to actually keep it deployed. And then if it in cases that your data drift is happening, that means you're given with a different data, then you have to make sure that you are capable enough to perform automated model training. So with the systems where you deploy your models, that's capable enough to train your models automatically, and you don't need to manually intervene every time your results drop. So these are some standard machine learning deployment strategies that you employ when you work with high-end models. Let's talk about transfer learning. We earlier saw how transfer learning can be used in cases where you can use pre-trained models and then you can fine-tune it on your own tasks. So when I say pre-trained models, it means that there have been a lot of data sets which have been released online because machine learning and AI, there has been a lot of open and collaborative work that's happening over the past few years. So a lot of open data sets are released by companies which have been used and which have been used to actually uh, generate big models with larger combinations of CNN layers and RNN layers and transformers, and they have been uploaded online to be used by people for free. Like for example, YOLO has been trained on large amounts of data set with large amounts of convolutional layers, and it has been evaluated to show best performances, but it has been uploaded online for free so that people can use it for their requirements. Now, let's say we use YOLO for a particular requirement, but it doesn't work well, right? Since it's uploaded online, we can actually download it and we can use it on our systems, and we can actually train it on a small section of data. We won't have millions and millions of images for our particular use case. Let's say I wanted to use it to localize images, organ images. Let's say I work with a medical research firm and I want to use it to localize organ images, but I don't have a lot of organ related images, right? I might have some few hundreds or a few thousands at max. So then in those cases, what I can do is I can take the checkpoints or I can take the saved models and then I can fine tune it. Fine tuning is basically training on a small amount of data set with a limited resource available on my own task. And when that happens, it allows my model to learn on additional data on top of its pre-existing learnings. So it does not forget its existing learning. Whatever it has learned online by using those large amounts of data, it does not forget that, but it allows to learn additional information, which helps it perform better on our tasks, right? Your model can learn more quickly and effectively on your specific task. This will also help you prevent overfitting because your model has already learned general tasks, right? If you give it small data and if you allow it to train from scratch, it can actually overfit on your data. So in order to allow not that does not happen, you don't give it to train from scratch, but you likely use it to train from a pre-trained checkpoint. This is the task of transfer learning, which has been readily employed, especially with transformers and in NLP. And now this technology has been used in computer vision applications as well. So the advantages include you speed up the training process because now you don't have to keep on training it on large amounts of data, and thus you don't need to wait for ages for your models to train. You will definitely get better performances, and you will be able to handle small amounts of data set, because if you don't have a large amount of data set or if you have a limited data available, you'll still be able to get comparable performance. Now that we have seen how computer vision models are trained, how these are deployed, what are the different types of computer vision tasks, what are the different deep learning models which are used for image and videos, let's look at some of the challenges that come with computer vision, right? So some of the challenges that come are, first becomes the hardware implementation, because since this model is heavily dependent on image and video inputs, if let's say your cameras are not installed properly, if some of the cameras in between are not working, if it does not cover all angles, or if some of them give blurred outputs, then your input data becomes very difficult to be passed on to your models, right? Then comes the problem of high computing costs, because in order to process these images and videos, you need to have high-end GPUs and you need to keep on having a machine where you can deploy these models. There's also the problem of lack of quality data, because you might get data with a lot of background noise, blurred images, low resolution images. You might have certain cameras which are not working. And then if you don't have proper quality data for training, you will definitely see suboptimal results in your performance. Then there's a problem of complexity to scaling of larger resources, because when you want to implement this, let's say you want to implement your traffic jam surveillance program to a, you already have it in your city, you want to implement it in two different cities, right? Then it becomes very difficult for you to do that, because the installation of cameras and the setting up of hardware resources and including all of that data, training on all of that data becomes difficult. So scaling becomes difficult with computer vision related tasks. There are a lot of improvements that are happening day by day, and we can see that this computer vision based models are moving ahead. There has been a lot of improvements in medical imaging tasks. There's been a lot of improvements in the generative AI domain, such as DALI, which I talked about, which can actually generate images from text. There has been improvements with 3D modeling. So now you can effectively generate 3D models which are very accurate and which can help you visualize certain details clearly. So product designs have become very easier to do these days because of the applications of 3D modeling. And you can also perform edge computing, where you don't need to send all the data to the server and wait for network calls and wait for it to actually take time and then perform computation. You can save that bandwidth and you can keep the data stored on your devices. Let's say if you're working on a mobile on facial recognition, then you can keep that system and software stored on your mobile. So every time you just look at your mobile for facial recognition, it just pops up in within a few seconds. So it doesn't need to send it to some cloud server and wait for some API to be getting called. We've already talked about a lot of applications in security, in self-driving cars, in healthcare systems. There's another field where computer vision tools are recently growing that involves the applications of augmented reality, where now that metaverse is also being considered and a lot of applications have happened in the AR VR world. It has been seen that computer vision applications of identifying objects, identifying images, tracking objects, tracking videos, segmenting objects specifically, where you actually segment those objects from the context and you replace them with some other objects. These have been used in augmented reality based applications and are used in video game scenarios as well. So we have seen a lot of different applications of computer vision, and this is a growing trend. And a lot of different models are coming up. So we talked about models like CNNs, right? Similarly, there are GANs, which are generative adversarial networks, which have both discriminator and generator models, which tend to identify the differences between real and fake images. So you can actually use GANs for tasks like image generation, where you can ask it to give a textual description, give an output image, And you can ask it to generate an image, and you can actually identify the difference between the generated image and the actual image. Then there are models like variational autoencoders, which encode your images and then generate multiple variations of that to identify on how different those variations are with respect to your original encodings. And the way the models are trained, it learns to encode and decode those images in a way that the output variations are very similar to the input structures. So along with these different models like CNNs, GANs, variational autoencoders, diffusion-based models, which are being used in computer vision, along with these, if there are textual-based tasks that are related, such as image captioning and video captioning, then we also use the inclusion of RNNs and transformers, which help you perform different kinds of sequential incorporation of textual embeddings. And then they help you decide the right set of textual outputs. So these are the few applications when it comes to computer vision and when it comes to actually deploying these computer vision related models.